Hey Phys 1 kids, Campbell here. In our fourth video on energy, we're going to talk about what happens during collisions. Now in our last unit, we talked about the law of conservation of momentum, and that's always the best way to solve for information like speed after a collision. Because there are different types of collisions, and we only talked really about totally inelastic collisions in that unit. But today we're going to talk about the different types. So like I said, momentum is always conserved in a collision, always, provided there's no external forces. But usually when we talk about a collision, we're only talking about external forces. Now, in an inelastic collision, mechanical energy is lost. Some of that mechanical energy gets converted into thermal energy. Like if I bounce this ball, it will not come back to the same height I dropped it at, which means that when it struck the table, it must have lost some of its kinetic energy or some of that mechanical energy, because not all the kinetic energy was able to be converted back into gravitational potential energy. And what happens during a collision is you start with when there's that force of impact, we start molecules inside the objects vibrating. And when those molecules start moving faster, that's thermal energy. Thermal energy is the kinetic energy of the molecules inside a substance. So we lose mechanical energy to the transformation of generating thermal energy. Now, in our last unit in momentum, we talked about perfectly inelastic or totally inelastic collision. That's when objects stick together. But most collisions in nature are inelastic. There's some loss of energy, whether they stick to each other or not. An elastic collision is one in which energy is conserved. Mechanical energy is conserved. Total energy is conserved no matter what. But in an elastic collision, mechanical energy is conserved. Now, the biggest mistake you're going to make is you associate elastic with like rubber bands, elastic bands, which are like stretchy and bouncy. But elastic in physics does not mean bouncy. Yes, this ball bounces, but that is not an elastic collision with the table because it's not coming back to my hand. That is an inelastic collision. So elastic does not mean it bounces. So anytime objects collide and they bounce apart, usually that's going to be inelastic. It's very rare that is elastic. So let's take a look at losses of energy in totally inelastic collisions. So here's a case where I have two train cars that are moving towards each other and they collide and then they get stuck together. And we would find their final velocity using conservation momentum. Momentum before equals momentum after. So just like we did in the last unit. But what I want to know is how much kinetic energy do we lose in this collision? Because that kinetic energy is generating thermal energy. In fact, if we could touch the cars, we would feel some heat. Well, to do that, right, the first thing we want to do is find out how much initial kinetic energy do we have. Well, we have two objects moving, so we have two different kinetic energies. Does it matter that one of the boxcars is moving to the left? Well, it does in momentum, right, because momentum is a vector, but not kinetic energy. So we're just going to calculate 1/2 mv squared for the one, we'll call that for mass 1, and we're going to add to that 1/2 mv squared for the second one. So it doesn't matter. Kinetic energy, there's no negative kinetic energy. It's either has it or it doesn't. All right, so our initial kinetic energy is 1/2 the mass of the one car, which is 2 times 10 to the 4th kilograms, times its velocity squared, which is 1.5 squared. To that, we're going to add the other kinetic energy, so 1/2 the mass of the other car, which is 4 times 10 to the 4th kilograms, times its velocity squared, or really the speed squared, because it's a scalar, 1.1 squared. Well, if you plug that into your calculator and you solve, you'll find that you're going to get 4.7 times 10 to the 4th joules. It's a big number, right? They're big masses, very massive. Our final kinetic energy is our kinetic energy of the cars coupled together. So 1/2, and it's going to be the total mass, so the mass of 1 plus mass of 2, because they're stuck together. So we're going to treat them as one system, times their final velocity squared, which we would have found using the law of conservation of momentum. So 1/2, so we're going to take 2 times 10 to the 4th, and we're going to add to that 4 times 10 to the 4th, fourth, which would be 6 times 10 to the fourth. And we're going to multiply by 0.25 squared. Again, negatives, there's no negative kinetic energy, so get rid of that negative. This total is much smaller, right? It's 1,900 joules. Wow, that's a lot of energy lost. In fact, if we subtract our numbers, the change in kinetic energy is 4.5 times 10 to the fourth joules. That's how much kinetic energy we lost, right? It's final, I should go final minus initial, right? So that's a negative. Now, I said you can't have negative kinetic energy, but you can have a loss, and that's what that negative represents. So what that means is I have generated thermal energy in the amount of 4.5 times 10 to the fourth joules. That's a lot of heat, man. So anytime I have a collision, almost always it's inelastic, whether it's totally inelastic or just partially inelastic. And in the process, I lose kinetic energy and I generate thermal energy. Let's look at the special case of elastic collisions, these very rare, ideal collisions, physics fantasyland collisions. In an elastic collision, we, of course, obey the conservation of momentum theorem, which we always will, inelastic or elastic. But we also can use the law of conservation of mechanical energy in that the kinetic energy before has to equal the kinetic energy after. So if we take a look at this example, I have object 1 moving with an initial velocity, and it's going to strike object 2, which is initially at rest. Now, in order for this to be elastic, the energy that gets compressed or stored in the compressed bonds have to go back into the two balls when they leave, because the energy of the balls has to stay constant. So afterwards, I have both balls moving, maybe, and so I have some velocities for both my balls, but they're not stuck together. In an elastic collision, they won't stick together. They will come apart. But remember, just because they come apart doesn't mean it's elastic. In an elastic collision, the initial and final kinetic energies have to be identical. So in this case, we have the law of conservation of momentum. We have an initial momentum equaling the final momentum of both objects. And we have energy. The initial kinetic energy of the one ball equals the final kinetic energy of the system, which is both balls moving. Now, if you think about this, if we tried to solve this with momentum, and I only had the initial velocity, or the initial momentum of the first ball, and I didn't know the final velocities of the two balls, I couldn't solve for this with just using conservation of momentum because I need two equations. But with using the law of conservation of energy with momentum, then I have two equations. So I can come up with ways to solve for both velocities, even though I only know one. So for our elastic collision, if we combine the energy and momentum equations together, and to solve for a final velocity of the first object, the one that was moving initially, and the final velocity of the second object, which was at rest initially, we can come up with these equations. Now, it takes a lot of algebra to get here. I will tell you, I had two students many years ago who really wanted to do the algebra. They loved their math fanatics. And it took each of them an entire whiteboard to get here. One did the first one did the second one. They got here, but it took a while. So these are equations to write down. And remember, so for an elastic collision, if the first object is moving, the other one's at rest, the final velocity of the first object will be the difference between the masses. So mass 1 is the one that was moving, minus mass 2, divided by the sum of the masses times that initial velocity from that first mass. The second velocity of the other object, the one that was started out at rest, will be 2 times the mass of the first object, divided by the total mass of that system, times the initial velocity of the first object. So these are handy dandy equations. And now we're going to take a look at how would we use those. So here is a scenario where I have an air hockey table and I have one puck that's moving to the right at 2.3 meters per second, and it makes a head-on collision with an object that's at rest. And I want to know, what is the final velocity of each puck? Well, if we use our equations, we want to find the first one. Remember, the first one, the final velocity of the first one is the difference between the masses divided by the sum of the masses times the initial velocity of that first one. Well, they're identical pucks, right? Which means that their masses are the same. So, I mean, I don't have numbers here, but it doesn't matter because their masses are the same. And so what does that mean? Well, that means that this is going to be 0 meters per second. Interesting. We'll talk about that again in a sec. The velocity of the second one, remember, is 2 times the mass of the first one over the sum of the masses of the total system times that initial velocity of the first one, which was 2.3. Now, if you think about this, if their masses are the same, so m1 equals m2, then the final velocity, right, this would be 2m over 2m, right? M plus m is 2. So those are going to cancel times 2.3. So that means that's going to be 2.3 meters per second, and they're going to go to the right. Now, think about this. And think about what you did in that momentum activity on the first day of the momentum unit. Remember how you had one car moving and one car at rest, and you did the magnet sides together? Remember that one car that was moving stopped, and it transferred all its momentum to the other car, which went off. So one went and the other one stayed. Boom, 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 boom. Well, those were elastic collisions, and that is true. Anytime you have an elastic collision where one object's moving, the other one's at rest, and they have equal masses, they have to have equal masses, then one transfers all its momentum, all its energy to the other. But that has to be equal masses. So this scenario is true only for equal masses. If you remember when we had the unequal masses, then one didn't stop. They both kept going, but so they were sharing their velocities or their momentums and their energies. So when they have equal masses, one stops, the other one goes, and it's a complete transfer. So we just proved it by using that equation. All right, fill out your WSQ. We're going to do some more of this in class, so I'll see you in class.